Let's take a moment and explore step functions. So before we go into a whole lot of detail, let's discuss what a step function is. So by definition, the unit step function, we use u of t, is a piece function where the function is equal to 0 if t is less than 0, is equal to 1 if t is greater than 0. So if we look at a graph of this, then if we're to the left of 0, if our time is negative, we're 0. If our time is positive, then we're 1. So this is kind of works like a switch. If t is less than 0, we're off. If t is greater than 0, we're on. Well, sometimes we want that switch to be turned on sometime other than at 0. We might want it to be turned on at t equals 3. So what we can do is we can adjust the step function. We can slide it to the right 3 units. You remember from translations that if we add or subtract something directly to our independent variable, that creates a horizontal translation. If we subtract 3 from our independent variable, it shifts us to the right 3 units. So in terms of our plot, what that would look like is when we get to 3, notice if we put, let's say, a 2 in for time, 2 minus 3 is negative 1, so for there, our y value is 0. In fact, any number less than 3, when we substitute that in, is going to give us a negative answer. And when t is negative, we get 0. So we're 0 to the left of 3. Any value that's bigger than 3, this is going to be a positive. So we're going to get 1. So we're going to be 1 from there to the right. So how do we write that? Then we translate everything. So if we're replacing this with t minus 3, then we would replace t with t minus 3 here, t with t minus 3 here. So essentially this would become t is less than 3, t is, excuse me, t is greater than 3. So when t is less than 3, we're at 0. When t is greater than 3, we're at 3. So we can make that generic. If we want to turn our switch on and off at A, then our step function u of t minus A would be 0 when t is less than A, 1 when t is greater than A. So that's going to be our step function. So what about the transformation of that step function? So to take transformation of any function, I'm going to use 3 for now, and then we can generically change that to A. Then to do a transformation, we integrate from 0 to infinity, e to the negative st times our function. So if we think about our function, then from 0 up to 3, from 0, notice our integral starts at 0. So we're starting here. So from 0 to 3, our u value, our function value is 0. 0 times e to the negative st would just be 0. And then from 3 to infinity, our value for u is 1. So 1 times e to the negative st is e to the negative st dt. The 0 times anything is 0, so we get 0 for that. And then we just need to integrate here. Let's see, if this is going to be e to the u du, we need to pick up a negative s here and divide by negative s here. So we have a negative 1 over s. The integral of e to the u du is e to the u. And we're evaluating that from 3 to infinity. Now, technically, we're evaluating it from 3 to n and then letting n go to infinity. but for short, we'll kind of go through this roughly. So this is going to be -1 over s. If we put n in and then let this go to infinity, remember, if we have a negative exponent, this is actually going to be in the denominator. If we're letting time get closer and closer and closer to infinity, that's going to 0. So that's what happens as we go to infinity. And then if we plug a 3 in, we would have e to the -s times 3. If we simplify this, that 0, a negative times a negative will make a positive. 1 over s e to the -3s, or we could call that e to the -3s over s. So that's what we get when we do the transform of u to the t minus 3. E to the -3s over s. So generically, the transform of u of t minus a is e to the minus as over s. So now that we see what the transformation is, let's look at a quick use of this. So let's suppose that we have some function. Let's call this function f. And for a while, this function is negative. It's running along here negative. And then at some time a, it goes positive. So you can think of this as a thermostat. Your thermostat in your house is reading the temperature. As long as the temperature is below a certain value, we don't want it to turn on. What we want to happen is there not to be any air conditioner running as long as our temperature is below that value. Once it gets to that value, then we want to turn it on. We want to turn on our switch. So we just imagine that our temperature, we're not worried about it for a while. And then once we get to A, now we are concerned about it. So we're not going to get in right now about, well, what does the air conditioner do to the temperature once we exceed that and once it turns on and all of that. But just imagine in certain situations, sometimes we want to ignore part of our functions, or we want to imagine it to be 0, and then for the rest of it, then we want to keep that function. So we can use a step function to transform this function f of t into this function on the right. We call that g of t or whatever. So imagine this section, if we took our original function and multiplied it times 0, it would give us this. If we took our original function and just multiplied it by 1, it would keep what we have. So we have a tool now that will work as that switch, that will be 0 to the left of A and will be 1 to the right of A. So this function or this graph could be f of t times u of t minus A. If t is some number over here, then that's going to come out to be negative. And when when we have a negative value in here, we get 0. If we have a value that's bigger than A, if t is bigger than A, this is positive, and u of a positive number is 1. So that gives us 1 there. So that would basically turn our function off to the left of A. It would turn our function on to the right of A. Just as a reminder, remind us what our step function t minus A looks like. It's 0 when t is less than A. It's 1 when t is bigger than A. Well, sometimes we might have a function that we need to turn on for a little while, but then turn it back off. For example, we might have a function that does this. And I'm just going to call this A and this B. So we might want to switch to have our function turned off until we get to A, and then turn it back off once we get to B. Oops. So between A and B, we want it to use our function. So if we call this function f, then in this section, we want f to be multiplied times 0. In this section, we want our function just multiplied by 1. And then in this section, we want it to be multiplied times 0 again. So we have two different values, so we may have two different steps, t minus a and t minus b. And both of these are multiplied times our function. So let's see what each of these are going to do, and then let's see if we can determine how we can use these two in order to produce this graph. So if we have u of t minus a, then when t is less than a, this is going to give us 0. When t is greater than a, that's going to give us 1. For this one, when t is less than b, we're going to get 0. When t is greater than b, we're going to get 1. So let's see what those graphs would look like. I'll just kind of sketch those real quickly. So if we multiply our step times our function, then when we're to the left of a, we're going to have 0. When we're to the right of a, we're going to have our function. So our function is doing this. So that has the left part correct, and it has between a and b, but that includes some stuff over here that we don't want. We don't want that part to the right of b. Now let's look at what this other one does. So this other one says if we're to the left of b, we get 0, so 0 times anything would be 0. When we're to the right of b, we get 1, so we're going to do 1 times our function, and our function does that to the right of b. So the question is, how can we combine these two to get the middle turned on, but the edges turned off? To get 0 here, 0 here, and then just that hump in the middle. Well, notice if we take this graph and subtract that one, in this first section, any 0 minus 0 will give us 0. In the second section, this hump minus 0 will give us that hump. In the section on the right, this and that match, so anything minus itself will be back to 0. So if we want that window from A to B, then we can do u of t minus a times our function minus u of t minus b times our function, minus our function. So that will give us that middle window turned on, everything else turned off. So we have a special notation for that, and it's called the window function. So the notation we use is this. So from A to B, t, the way we, it's u of t minus a minus u of t minus b. And that's equal to a piece function that is 0 when our t is less than a. It's 0 when t is greater than b, but it's 1 when t is between a and b. So that's our window function. So now that we've looked at step function and the window function, and we've looked at how to get the Laplace transform of the step function, let's look at how we get the Laplace transform of the step function times another function, because normally that's what we're going to have. The step function is useful. It turns the switch on and off, but normally we're not just going to Laplace zeros and ones. We're going to Laplace turning a particular function on or turning a particular function off. So if we have, for example, the function u of t minus 2 times g of t, and we want to do the transform of that, then remember how we do a transformation in general. Laplace transformation is we do an integral from 0 to infinity e to the negative st times our whatever we're transforming. So u of t minus 2 times g of t dt. So let's look at what our step function does for us. So keeping in mind that u of t minus 2 is the step function that is 0 when t is less than 2. It's 1 when t is greater than 2. So when we are from 0 to 2, it's e to the negative st times 0 times whatever our function is. Well, anything times 0 is 0. And then we go from 2 to infinity. In this case, u is 1, so is e to the negative st times 1 times g of t dt. So the first integral, when we integrate 0, that's just 0. But to evaluate the second integral, remember our definition, the Laplace transform goes from 0 to infinity. If this was going from 0 to infinity, then this would just be the transform of g from t to s. But it doesn't start at 0, it starts at 2. So we can do a shift. We can let t equal v plus 2. So by default, the dt would equal dv. Notice what that will do for us. If t equals v plus 2, or you could say v equals t minus 2, then if t is 2, then v is 0. So we can just do a change of variable. So if we're going to change dt to dv, and then here this e to the negative st, in place of t, we're going to put v plus 2. Here we're going to go from not 2, but from 0 to infinity, because this is a t value, this is a t value. So when t is 2, we said v is 0. And then in place of t here, we're going to put v plus 2. Okay, so since we have a product here, we can distribute that. That's minus v minus sv times minus s times 2. When we have a sum or a difference in the exponents, we can write that as e to both powers, because when you have parts, when you multiply like bases, you add the exponents. So you could also break it apart as a product of like bases. So we could call this e to the negative 2s times e to the negative sv times g of v plus 2 dv. Now keep in mind our variable is v. So s is a constant in terms of our integral, so we can pull e to the negative 2s out front. This will be times the integral of 0 to infinity e to the negative sv g of v plus 2 dv. So let's make an observation. Let's call g of v plus 2 just f of v. That's just a mapping from one function to the other, where basically we've shifted over a little bit. This is just a horizontal transformation to the left 2 units. So we can replace g of v plus 2 with f of v. So this part is just the Laplace transformation of f of v. This is just simply how you transform this function. E to the, instead of V's, or instead of T's, we have V's, but this variable match. We're going from 0 to infinity. So that whole thing, by definition, is just the transformation of that function. And then out front, we have an e to the negative 2s. If we change back to our original function, then f of v, we said that's just the function g of v plus 2. So if we have a step function times another function, and we want to take the Laplace transform of it, then the way we do that is it's e to the 2 was our a value, so e to the negative as times the Laplace transformation of g to the v plus a. So we don't transform v, so it's supposed to be a 2.